In the previous lecture, we discussed about the magnetic reconnection and how the electrons or the charged particles are accelerated at the reconnection region. In this lecture, we will see under which condition, what are the conditions under which this particular acceleration can happen. If we write down the equation of motion of the charged particle being accelerated at the reconnection region or neutral sheet, can be written as your acceleration minus the loss term. So now, what is acceleration? So as we saw, as a magnetic field lines are convected into the neutral sheet, is going to develop an electric field, and that electric field is going to accelerate the particle. So this is going to be nothing but my EE. And the loss term, we discussed towards the end of the previous lecture, the loss is because of the collision of the plasma, because of the collisions between the plasma. Therefore, the collision is one which is going to stop the flow of particle or going the acceleration of the particle. So I can always write the loss term as a collision nu c, which is the collision frequency, mass of the particle, and the velocity. So nu c is the collision frequency. And this decides whether this nu c decides whether the particle can be accelerated to the reconnection region or not. Now, to find the collision frequency, we should know the mean free path also. So now let us, in the picture we have as the particle moves along the neutral sheet. So what we will see as a mean free path is the distance after which the particle loses its initial direction. That means when the velocity, because the particle travels through the neutral sheet due to collision, when the velocity, final velocity, let me write a VF, becomes perpendicular to my initial velocity, at that distance, the particle loses the memory of the initial direction, and we call that distance as your mean free path, and the time taken for that is your collision time scale, and the inverse of the collision time scale is your collision frequency. So the particle eventually gets scattered, multiple scattering, and eventually it loses its memory of its original direction. So we can always say, so the mean and each collision is going to impart a component of the perpendicular velocity. So the mean average square perpendicular velocity attained per second by the particle can be written as d by dt to delta v perp. This is a perpendicular velocity I'm saying, whole square. And we are taking the square because we don't want to have the sign convention here, because we consider both the cases, whatever the perpendicular above would globe to be the same. So we don't want to have this sign. So we are taking a v square. Now after spending a time t, say a collision time scale tc, so then after spending the collision time scale tc, so this is going to become my original velocity v squared. And when it happens, we say the particle lost its initial memory of its direction, and that gives rise to a collision frequency time scale we can calculate. So basically, to identify the Tc, we need to know what my delta v perp square. Now let us try to find out how to do that. So to find this delta v perp, we will before we go into v square, we will say what is the perpendicular velocity component imparted by per collision as the particle moves along the plasma. So to make our calculation simple, we are going to consider all the particles are going to have a same charge, and all the particles are at rest. None of them are moving except the particle which is under consideration. So in that case, I can always draw the figure, and all the particles are going to have the same charge q, and this is the particle of consideration with a charge q moving at a velocity v and at a distance r, and so this is the impact parameter b, and Now, as the particle moves, so let this be the angle theta. So then we can say the force, the component of force along the means perpendicular, the perpendicular component of force acting here F will be q square sine theta by r square. Well, and we have the velocity v is equal to dx by dt. So this is the x direction I'm saying. Yeah. So dx by dt, therefore dx is equal to therefore dt is equal to dx by v. So this is the perpendicular force acting because of this particle, and this is the time scale, typically dt, which is going because of the motion of the particle. So the perpendicular impulse will be f dot dt, which is nothing but the perpendicular momentum gain. So this is going to be m into del v is equal to this over the time scale dt. So now I have to integrate over the time scale for the entire duration of it. So this is what the perpendicular momentum acquired by the particle as it moves through the plasma. So now let us substitute this value, this known whatever. So this will be equal to, okay, fine. This is q square sine theta divided by r square into dx by v. And now from this figure we know your r is nothing but your r is b by sine theta, and your x is equal to b by tan theta, and therefore dx is equal to b by tan square theta sec square theta d theta, and that's equal to b by sine square theta d theta. Perfect. Yeah. So, and now substituting all these values here, I can take my q square outside, and my v also I can take it outside. So sine theta by r square is so this is b square into sine square theta into dx is nothing but b by sine square theta d theta. So sine square theta cancels. So this is going to be q square goes off. So q square by vb integration of sine theta d theta. Well, the limit is 0 to pi. Therefore, this becomes equal to 2. So this is equal to 2q square vb. Or I can write, or from here I can write, therefore, the perpendicular momentum attained per collision will be 2 times q square mvb. So let me note down this value, these expressions. We may need it later. So what are the things we need is, so we will have d by dt of, delta v perp whole square, tc is equal to v square, and my del v perp is equal to 2q square by mvb. So let this be 1, let this be 2. Fine. And remember, okay, I can even draw the figure. So You can draw the figure that is your particular Q, and this is Q, and this is theta, R, X, this is velocity V. Yeah, fine. And this is your B, parameter B. Well, fine. So great. Yeah, fine. Let this be here. Well, to find the rate of the mean change in the perpendicular velocity attained as the particle moves along the plasma, so we need to find out what is the total number of collisions happening per second. That means we have to consider a volume, and we have to consider a cylinder with a length V, and I'm going to consider the hollow cylinder with a radius, my impact parameter B, and this distance is dB. So, and the plasma density in the cylinder, we will consider it as N. Therefore, the number of scatterers in this volume is nothing but the volume of the cylinder. The volume of the cylinder is what's that? 2 pi B V into dB, and the total number of scatterers in the volume will be the number of scatterers will be 2 pi B V N dB. Good. Fine. So now this is the total number of scatterers, and under each scattering is going to impart a perpendicular velocity. And now to find out the mean square perpendicular velocity attained per second, all I have to do is integrate this over some B min to B max. We will see that what it is. We will not go detail into it. I will just mention what it is later on. B min to B max, and then the total number of scatterers is 2 pi B V N dB, and now each scatter is going to impart a perpendicular velocity. So we are going to the mean square perpendicular velocity. So this is going to be del V per whole square. Good. So now this del V per whole square, we can just take it from our equation already we have derived. So this is going to become, this will be, so this is V square, so this will be 2 to the 4 and 8 pi, and then there's a Q square is there that will come out, and then we have N here, and this V, and while you're taking a square, this is going to become as a 1V, so this is going to M square V, and this B square and B will come as dB by B. B min to B max. Right? Yeah. Perfect. So, and this is nothing but 8 pi Q square N by M square V ln of B max by B min. Well, this B max and B min is, there is a limit on your minimum impact parameter and the maximum impact parameter. I'm not going into detail of it. You can go to the literature and try to find out what it is. For time being, we can always consider this as some value 8 pi Q square N, which is more important for us, M square V ln of lambda. So we are having my mean perpendicular velocity attained as the plasma, as the particle moves through the plasma is nothing but, so, sorry, this is your, sorry, I missed it, d by dt is per second. We have taken the velocity. Okay, fine, will be 8 pi q square n divided by m square v into ln of gamma, sorry, ln of lambda, sorry. So, and this is an interesting expression we got. Fine. So when now I can always plug this value here and I can always find out my collision time scale or my collision frequency. So when I plug back, what I'm going to get is 8 pi q square n ln of lambda divided by m square v into Tc is equal to V square, V. So therefore, my collision frequency nu c, which is equal to 1 by Tc, that will be 8 pi q square n ln of lambda divided by m square v cube. So if you remember in the last lecture, we said, of course, this collision frequency is going to depend upon my plasma density, and that will inversely goes as my velocity of the particle. So the higher the velocity, the collision is going to be less. And this is a very interesting relation. Why it is interesting? We'll see. So if you see this equation carefully, what you see is nu c is inversely proportional to the velocity v square. And if you see here, suppose let us say for initially the plasma started accelerating. So now as this acceleration happens, the velocity is going to increase. As the velocity increases, my collision frequency is going to reduce. So the loss reduces, and so eventually what happens? The particles keep on accelerating. What we end up in a runaway process. So the particle can actually accelerate to much higher energies, and what finally is going to limit is your what comes is your plasma instabilities, or otherwise the field which is generated by the movement of the current cannot be exceeding the actual field. So then once it reaches that limiting stage, the acceleration is altered. So, and these are the limiting process, and till then there will be a runaway process and the electrons will keep on accelerating. Okay, for acceleration to happen, this quantity should be greater than 0. That is your E minus nu c. Oops, sorry, we have to mention this charge we have kept as q here, so we will make it, we wrote here later on as a q. So acceleration will be QE minus nu c mv has to be greater than 0. Now I'm substituting this nu c from here. What you are going to get is QE minus 8 pi q square n ln of lambda divided by m square v cube should be greater than, v cube should be greater than 0. So now I can always have a critical velocity. So by equating it to 0, I can always have a critical velocity. Once the plasma has a velocity greater than that critical velocity, then the plasma can undergo acceleration. Fine. So that's going to be your QE is equal to 8 pi q square n ln of lambda divided by m square and the critical velocity vc cube. So therefore your vc cube is equal to 8 pi cube n ln of lambda divided by m square e, or my vc is nothing but 1 cube root of, so this is the critical velocity. So, and this is the velocity if for a given plasma with a plasma density n, plasma density n, the particle can be accelerated at a recollimation region if the velocity is greater than this critical velocity. So once this velocity is greater than critical velocity, the plasma can keep on accelerating, because as it accelerates further, my collision frequency, your collision frequency reduces. That will increase the acceleration component. More this increase the acceleration part, so the particle will eventually go into a runaway process, as we discussed. So the charged particle, to get accelerated, it should have an initial velocity which should be at least this vc. If it is greater than vc, the electron can be accelerated, and as it's accelerated, the collision frequency goes down. As the collision frequency goes down, the acceleration will be further. So as we said, the electron can keep on accelerating until it reaches the limiting value. Now, if you assume a plasma to be a thermal plasma at temperature T, then we can write half mv square equal to 3 by 2 kT, and from here the V I can substitute here, and this expression will come in terms of temperature T, and then I can invert the relation and to say what should be the electric field should be generated in the neutral sheet so that the electron can be accelerated by your magnetic reconnection. So you can just plug in this V square here, and then what you will finally get is the critical field, which is called as your Dreiser field. Dreiser field, that is 8 pi cube and ln of lambda divided by 3 kT. So we can just substitute this and make your E as your ED, that's the Dreiser field. So now if the field generated, if it is larger than the Dreiser field, then the plasma can be accelerated and the magnetic reconnection can happen. Good. So these are the certain conditions under which your magnetic reconnection can accelerate the particle. And now in the next lecture we will see what is the time scale at which the particle will be accelerated. That typically depends upon the magnetic diffusion time scale. That's as the magnetic field diffuses into the neutral region, if you somehow try to find out an expression for this magnetic diffusion time scale, so that will give you a typical time scale of this particle acceleration to happen. Thank you.